We will solve two examples on non-homogeneous or inhomogeneous recurrence relations. Now for the first recurrence relation, first we need to rewrite the recurrence relation as an minus 2 an minus 1 is equal to 3 raised to power n. So it is divided into two parts. This part is the homogeneous part, and this part is in fact the function f of n. Step number 2, the characteristic polynomial. And how to find it? First, we will find it from the homogeneous part, which is x minus 2. And the second one will be obtained from f of n. And this is x minus 3 equal to 0. So this is the root obtained from f of n, and this is the root obtained from the homogeneous part. The roots are r1 is equal to 2 and r2 is equal to 3. Step number 3 is finding the general solution. And the general solution is called an. It will be constant multiplied by 2 raised to power n plus another constant multiplied by 3 raised to power n. Now for finding the constants, we will use two methods. The first method is not in your textbook. The second method is by partitioning the constants or dividing the constants into two parts. One part will be obtained from the roots from the non-homogeneous, which is f of n, and the other one will be obtained from the homogeneous. So let us give those parts name. Now this part is the responsible for the homogeneous solution. And this part, we will call it particular solution, which is obtained from f of n, particular solution. So for finding the constants, the second method that I will explain, first we will find the constant for the particular solution, and then we will find the constants for the homogeneous solution. So therefore, we will use C1, C2, C3, etc. for the homogeneous solutions, and we will use capital letter A, B, C, D for the particular solution. So I will change now this constant, and I will label it A, capital letter A. So what is these two equations? We will give them labels. The first one, we will label it ANH as homogeneous, which is equal C1 times 2 to the power n. The second one, we will call it also AN, but P as for particular solution, which is equal to A multiplied by 3 raised to power n. So we have two solutions, one for homogeneous and one for the particular solution obtained from f of n. For step number 4, now we will finding the constant, finding the constants. I will teach you two methods. One is not in your textbook, finding C1 and A, the two constants at once. So method number 1. Number 1, finding C1 and A from boundary conditions, and these boundary conditions including the initial value from boundary conditions. Now we have two constants, C1 and A, so we need two boundary conditions. One is already the initial value, A0 is equal to 5, which is given. The other one, we need to find it. So since A0 is given, Let us find A1 because we need another one, two constants, we need two equations. So how to find A1? If you go back to the recurrence relation, the original one, A1 is given to you as 5. So how to find A2? A2 is equal to 2 times A1 plus 3 raised to power 2 because n is 2. So we will write it now here. So it is 2 A1 plus 3 raised to power 2, which is equal to 2 times 5 plus 9. It's equal to 19. From these two boundary conditions, we substitute into the general solution, which is this one. This is the general solution. So for A1, A2, sorry, we don't have A0. This is A0, this is okay, this is A1 and A2. So for A1 is equal to 5. When you substitute, we will have 2 C1 plus 3A is equal to 5. This is equation 1. And for A2 is equal to 19, we have 4 C1 plus 9A is equal to 19, and this is equation number 2. And these two equations are obtained from here. When C1 is 1 and when n is 1 and n is 2. Solving for the constants by using the calculator, the value of C1 is equal to minus 2 and the value of A is equal to 3. So the solution AN is equal to minus 2 times 2 to the power n plus 3 times 3 raised to power n, and this is the general solution found from the boundary conditions. Method number 2. Number 2, finding the constants, finding A from the particular solution ANP and C1 from ANH. So we will divide the constants into two parts. First, finding finding C1. Yeah, okay. First we will finding A from ANP. Let me just change the title. It is finding C1 from the initial value, okay? From the initial value. So finding A from the particular solution and finding the constant from the initial value. So let us find A from A and P. And remember, what is the value? What is equal to? This is equal to A times 3 raised to power n. So what is the recurrence relation we have? We have AN minus 2AN minus 1 is equal to 3 raised to power n. This is our original recurrence relation, which is this one. We will substitute for AN from the particular solution, and we will substitute for AN minus 1 also from the particular solution. So we will have here A times 3 raised to power n minus 2 A multiplied by 3 raised to power n minus 1, and this is equal to 3 raised to power n. Take a 3 to the power n common, so you will have A minus 2 over 3A equal to 3 raised to power n. Why we have minus 2 over 3A? If you take a 3 to the power n common, what remains in this term is a 3 raised to power minus 1, which is equal to 1 over 3. And 1 over 3 times 2, it will be 2 over 3. Solve for this equation. So you can divide both sides because it should be positive. You divide both sides by 3n. You will have a minus 2 over 3a is equal to 1. So 3 or 1 over 3a is equal to 1. And from here, make a space, and from here a is equal to 3. So what will be the recurrence relation? The general solution, an is equal to c1 2 raised to power n plus 3 times 3 raised to power n. Now step number 2 is finding c1 from the initial value, which is a1. And if the initial value is a1, then we have a1 is equal to 5. So we will have 2 c1 plus 3 times 3, which is 9. It's equal to 5. And from here, c1 is equal to minus 2. So therefore, now an is equal to minus 2 times 2 to the power n plus 3 times 3 raised to power n, and this is the general solution. Now if you ask from where did we get this equation? From here. If a1 is 5, so n is 1. So you have c1 multiplied by 2 raised to power 1, which is 2c1. And here you have 1, so 3 times 3 is 9, and it's equal to 5. And this will finish the steps. So as you notice that we are using two methods for the constants, one from the boundary conditions and one by using the particular solution.